seen it from the student version. Join. You want to click join. So I want you to click skip. Click skip, or did you log in?
I walked.
Find lesson. And press skip up here. So find lesson and press skip in the right corner. And then there's a thing called join. Join.
I guess I'm in.
And then go ahead and type those in. Yep, join.
So I'm going to assume that it's case sensitive.
You can try it. I'm not sure.
You can put it
Oh,
in
never
there.
mind.
Join.
Just
You got it?
Yeah, I'm
You
ready.
got it? And you can just put in your name. Yeah, and just join. Alright.
well, it doesn't let me do our case anyways.
Let me just try it. Think everyone's in. Okay. So, I tried to minimize the notes for this. So, I would like you guys to have enough room. This is a vocab sheet, the blue sheet that you're given. That's basically all we're really going to be taking notes on, because I would rather just discuss a lot of these topics because you've never learned them before. They're very interesting topics. They're cool. You get to learn about statistics, that kind of thing. But today and tomorrow is kind of like an introduction. So we're not going to be doing a lot of math skills today. Not a lot of hard ones, I should say. So this is going to be super important. Always have this out when we're doing the notes. And then I shortened the notes today because we're going to be doing a lot of discussion and experiments, kind of working through some things. Yeah, I got Justin Bieber up here. So interpreting data and normal distributions. I want you guys to take a second and write down here what you know about statistics, or what comes to your mind when you think of statistics. Is it baseball stats? Is it anything statistics? So go ahead and just type in anything that you can think of that relates to statistics. Like when you hear the word statistic, what pops in your head? It could be nothing. If you have no idea what statistics is, you can say, I have no idea. Okay, so we got Abby thinks medical research. That's great. Medical research, you need to know stats. Whenever you're in the medical field, you know, what's the probability of this happening to your patient? That's huge. And then we got charts. Okay, charts, definitely. Tommy doesn't know.
I have no idea.
You've never heard anything about stats before?
Nope.
You never like saw baseball stats or like your batting average and
Nope.
nothing? Crazy. Okay, well guess what? You're gonna learn about it. Chart, I got another chart. NBA because of the shooting percentages, which is really interesting because we're about to talk about those. Okay, so the shooting percentages and how many times you can make a free throw, very, very good. So I'm just gonna show you like a 2-minute clip on why statistics, why it's important, why we use it every single day. And then we'll kind of talk about it. Why? Wait. Can you hear it? Nope. I always show this video every year. I like it. He's a good explainer.
All right. Why statistics?
Statistics, the practice or science of collecting and analyzing numerical data in large quantities.
Why study statistics?
Oops, sorry guys. I was trying to make it bigger.
All right. Why statistics?
Statistics, the practice or science of collecting and analyzing numerical data in large quantities.
Why study statistics at all? Why do we have a federal statistical system? Why a census bureau? What good is statistics? To answer this question, let's first talk about something else. Why a microscope? Well, a microscope is used for studying things that are, as the name may imply, microscopic.
Microscopic, so small and fine as to be invisible or indistinguishable without the use of a microscope.
You need to look at something that's really, really tiny, too small for your eye to see, and you blow it up to a screen about getting big. This turns out to be really, really handy. If you want to study cells, for example, like bacteria, you want to understand food poisoning, you want to understand disease, you want to understand how viruses spread, you got to be able to actually look at them, to see them. If you can understand how big they are, how small they are, what their shapes are, what their form is, if you can get the form, you can get the function, and you can get some understanding. You want to build a microchip? You need a microscope. Now, that means that a microscope is really, really useful for looking at things that are too small. Now let's consider the kinds of questions that we answer with statistics. We talk about things like the population of the United States. The population of the United States. In 2010, there were 308 million people in the United States. You can't possibly know everyone. You can't talk to, you as a person, you don't have enough time in your life to sit down with everybody and learn their story. But, every 10 years or so, we at the Census Bureau ask a few questions of everybody. Age,
You will get
sex,
these when you're older.
birth,
I've got
where you live. These are
They
important things to
monitor
know.
things.
And with just those few questions, we can learn an enormous amount. You want to know where the hospitals go? You need to know what cities have a large aging population. You want to know where the schools go? You need to know where the cities and neighborhoods have a lot of really young people. These kinds of questions. And it's all kinds of things. Birth rates, death rates. You want to understand the labor force. That's a statistical question. You want to understand employment. You want to understand earnings. You want to understand national earnings. You want to understand these questions, accidents rates, all kinds of things that we publish statistics on, that we measure statistics. They're all things that are too big to see at one time. They're too big for your eye to see. 308 million people, all of different ages, all different sexes. We've got accidents happening spread out across a country of literally millions of square miles. It's too big to take in. But aha! A federal statistical system, statistics, we can take a slice of that country. Delicious! We can take a slice of the United States of America and we can shrink it down to a screen about yay big. I've got a bunch of them back here. When you can take a big thing and shrink it down small enough to study, to understand, or at least part of it, that's useful. That's statistics. So you want to understand that something that's too small, like a cell or a microchip, you need to blow it up, you use a microscope? Statistics is a macroscope. That's why statistics.
Okay, I just really like that video because I think it just explains, really well what it is and why we use it. It's super useful. Oh no, that's for you, kid. Yeah, you got all three of them.
Oh, three?
Yep.
What?
We'll talk about it. We will talk about it. We'll talk about it. But statistics is like one of my favorite topics in math, and hopefully it will be one of your favorite topics after this chapter, because you really don't need to apply any math skills that you've ever learned to this chapter. So it's like you're starting completely fresh. You don't need to know how to solve an equation for this. Well, maybe like one thing. Okay, one thing you have to solve an equation for, but it's brand new. You haven't learned this before, at least from my knowledge, on how to interpret data. Which, if you're going into a business field, any field really, you gotta know statistics. We, as teachers, do statistics on all of you. Where do you think those SAT scores come from? What's the average? That's statistics. What's the average in Illinois? What's the average here at Lockport? Those are all statistics. Okay, super, super important. It's basically how everything runs, is based off of statistics. And that's why we study it. This is just kind of something cool to see. I didn't really have you guys do anything with it, but it's the Census Bureau, which is what he just talked about. It's their Twitter page. And you can kind of see some statistics on here. If you click that link, I don't know, can you guys click it on there?
Yeah.
If you click it, you can like scroll through and it'll tell you, Texas is getting bigger. Every year it's getting bigger and bigger and bigger, and they're trying to figure out why. Okay, that's what statistics is all about. It's kind of cool how you can see that. I'm going to zoom you through the next one here. So I was just showing you on this page that you guys have the blue sheet, and I would definitely start filling it in from this point on. I'm just going to kind of prompt you on how to do it. I'm trying to eliminate notes, but have you guys still have something to look off of when you're doing your homework. All right, so we have something called discrete data and continuous data, which are the first two items on your blue sheet. Discrete data is going to be data that, let me show you, whose possible values are countable. And I believe countable is the word you're looking for in the blue form. Countable is that first blank. So if I can count it, like, hey, how many people are in this room? 1, 2, 3, 4, 5, 6. I can count 7, 8. I have 8 people in this room. That's countable. I can't be like, oh, there's a half a person right there. You can't do that. You can count them on your fingers. Whereas, so we have score of a basketball game, we have a team score, we have shoe size, we have the number of pages of the book. Now, on your notes, or actually on this next part, I want you guys to come up with an example. So, something you can count. Give me any kind of data that you can count. How many phones are in this classroom? anything that's countable. What can you count? Let me know what you guys get. Oh, you didn't. I do.
There are 2 trash cans.
There you go. That's an example. Go ahead and put that in there. I just want to see what you guys think, and I want you guys to like one of them. Yep. What does it say? Enter your input. Does all of you say that? You don't know what it says that.
Very fresh.
Let's see. Yeah, there you go. Okay, so when you guys are done, I want you guys to go ahead and like their favorite one. There's 1 fish tank, that's good. There are 2 trash cans, decorations on the wall, posters, pictures, decals. Those are great. Great options. You can like any one that you want, your favorite one. But yeah, anything that you can count. I'm still waiting on one. Mr. Dominici. How you say it? Dominici? Mr.
I thought it was Dominici.
Dominici. Well, see, my family is, yeah, we have the H. We have the H in it, so, yeah. All right, so maroon squares on the floor. Very good. Those are all data. You can count them. Now let's talk about what continuous is. It's the opposite. You can't count it. It's impossible to count that many. Okay, so something like the height of all the students. I can't physically, as I measure you, count all of that height because it goes from like 0.1 or 0.0001 or it changes the type. So same with temperature. It doesn't just go from 0 to 70. It goes from 0 to 0.5, 0 blah, 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 all the way up to 70. Same thing with running a race. The times are decimals. Okay, you can't count that. It's kind of like those intervals. So that's the next one on your blue sheet. They're data in which any numerical value within any range. So numerical, I think, is that blank right there. Numerical, you got it. Cool. So I want you to do it again, and I want you to give me an example of something that's continuous. So anything that basically has a decimal or something like filling a bathtub. Okay, it doesn't just like, I'm not like, what is that? I Dream a Genie or Bewitched, where like I can snap my fingers and the tub is filled. It takes a process to get there. Okay, so I want you guys to try to think of one. This one's a harder one. Think of anything that you can think that's continuous. What's something that like takes progression to get to?
I don't know.
So think about, again, temperature. Think about a race, like you're running. You can't count your time. You can't count how fast you're moving because you're going to continuously be moving. You could be moving faster at some points. You could be moving slower at some points.
Yeah.
Birth rate, hair growth. Hair growth, definitely. Shoe size is discrete.
Oh.
Okay, I can actually tell you what your shoe size is.
Car speed.
Car speed is big. Yep, car speed's definitely one. Filling a container is very good. Yeah, so again, you don't go from 0 to 180 or 0 to, I know you're never going to go that fast, right? Or 0 to 100 in like that. It doesn't just, it takes you a progress to get there. Again, if it takes some kind of progress to get there, that's what continuous is. Okay, you can't just go from 0 to 100 and out of nowhere. You have to progress to get there.
Yeah.
It takes more than a second. That's what I mean. Like it,
No.
so you're telling me that like it skips 1, 2, 3 miles per hour, just goes to 180.
Well,
Your car's like.
well, if you're in a Lamborghini, well, you'll be going
dash
fast.
on the R1.
Shoe size is not one of them.
That thing's fast. They showed the video of that one. Just like skips.
So if you're talking about your growth of your foot, yes. The shoe size, I can tell you. Like, hey, he has a size 8 foot and a size 9 foot. I can count that. Okay, that's a good question. So if you're talking, so Tommy, I'm going to elaborate on yours a little bit more. Shoe size, I get where you're coming from, but it's like if you're talking about how your foot grows from birth to now, that's different because you can't measure that. You can't count it. All right. Good, good, good. All right. Fill in the blanks. Let's see if you can kind of summarize what we just talked about. You want to take those things on the bottom and you want to, oh, you can see the answers?
We can see the no. Oh, yeah, we can see your answers.
You can see my answers. Why is that? It's okay. I'm getting used to this program too. Does it let you drag things?
Yeah.
Okay.
They told me I got 2 out of 2 already.
Good. So
Oh, I see now. Okay. Wait.
So I want you to try not to look at mine, because I don't know why it's showing. It should not show. But drag and see which one you think it is. I'm going to cover it up. I'm sure you're
Yeah.
inside. Okay, data who's countable, think countable, and then data that to take any numerical at any time. Did you get both of them right?
I got 1 out of 2.
How can you get
I
one
got-
out of two?
I got-
It's only a 50-50 shot. It's all or nothing.
I got 2 right.
All right, so here's what those pieces of paper are for. You have 3 pieces of paper. I want you to crumble all of them up. All of them. You crumble them up. And I know it's going to be your favorite game. And I want you to go to one of these lines and see how many times you make a basket. So go to one of the lines and see how many times out of 3 you can make a basket. There's one over there too. So Tommy, you can go to that one. So crumble it up, and I want you to see how many times you can make a basket. Go to a line and see. I already missed. I got 0 out of 3 right now. See who gets the most here. There we go. There's all those baskets up there. There's one
What
over
line?
here.
I don't have a line.
You can just go here. There you go.
Oh, that's
2.
gonna be easy.
Okay, so you got 2 out of 3. Remember that.
Let's say that's gonna be easy. That's still easy.
It's okay. Well, we'll see. We'll see. Count how many times you get, and then go back to your seat. Don't reach. Ah.
2 out of 3.
Okay. Awesome. Now go back to your seat and go ahead and put in what you got. 1, 2, 3, 0. Probably should have made it harder. A little bit further. All right. So you can see right here on your desktop that 50% of people in this room got 2. Okay, that's statistics. 50% of the people in this room got 2 shots made. One person got 0. One person got, nobody got, what's 6.7? Oh, 16.7% got all 3, which was only one of them, so that makes sense. Okay, so that's something that you can be using statistics on. Now to make that a little bit more interesting, relative frequency. That's what it is. How many times out of a total amount did that happen? Relative frequency is at 50%. 50% is the relative frequency because only there was 2 people out of 1, 2, 3, 4, 5, 6. There were 3 people out of 6 that made 2 shots. And that's why the relative frequency is 50%. And that's what we're kind of getting into today. I think on your blue sheet you have something to fill in here. Your relative frequency is going to be the number of occurrences. So we didn't get there yet, but it's the number of occurrences divided by the total amount of occurrences. So the number is what you would fill in. Now we're going to talk about kind of what Michael was talking about earlier with Michael Jordan. So go ahead and click that link. See if it clicks. And press the...
chart shows some of Michael Jordan's career statistics.
We'll just keep his on.
for free throw shots when he was on the Chicago Bulls basketball team. Determine Michael Jordan's Chicago Bulls career average for his free throw percentage and type your answer in the blank at the bottom of the chart.
Okay, so I'll explain what that is. You can turn yours off. You can turn your volume on. Press the play button and just don't listen to it. You can turn your volume off.
Your average is also known as the
Yeah, there you go. Okay, so that is actually Michael Jordan's statistics on his free throw shots. That's his statistics from the years that he was on the Bulls. If you're a basketball fan, then go ahead and enjoy this because I don't like basketball. So from 1994 to 1998, how many years was that? 1984 to 1998, how many years was that? 1994 to 1998.
14, I think.
14, 1998, yep, 14 years. How do you find the average of something?
Multiply it.
Not multiply.
Divide it.
Divided by the
You-
the amount.
Yes, you add them all up and divide by the total amount. So what I want you to do is find the average for Michael Jordan at the end of his career for the Bulls. What was his final average? This is accurate data. This is not just made up. Okay? What was his actual average? So all you gotta do is get your calculator out, add up all of those numbers on the right side,
And divided by.
and divide it by the amount of years. So 14.
That's right.
Do we have to put the 0 point, or can we just put the number?
You don't have to put the 0 point.
So just add up all the numbers and
Divided by the amount, yeah.
Isn't that like the mean or something?
It's the mean slash average. Very good. Mean, average is the same thing. So again, this is accurate data. This was Michael Jordan's average. And that's what we're going to be using a lot of, the mean, the average. And you're going to divide it by 14 years. Well, yeah, for the decimal. That's okay, we can still do it. Keep going. You just need to divide by 14,000. Because you moved the decimal on me.
Now what?
SAT. You have to divide by 14,000. Because yours is off. No, not 14,000. Yeah, you didn't put the decimals in. You have to put the 0 in, but you have to put the decimals in.
Oh.
It's okay, don't worry about it. What'd you guys get?
Oh, you're supposed to put decimals in?
Yeah, you put the decimals in, silly.
Nope, I got this.
Let's see what everyone else got. Let's see. It's okay.
I'll type it online.
Okay, so here's why. We said 14, and I know why we did that because we do 84 to 98. That is 14 years. But how many intervals are we talking about? If you count the tables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there's only 13. So you would divide by 13 instead of 14. So if you have a graphing calculator, you can just go up. Press enter and divide by 13.
that is genius, I didn't know that part.
But you missed the decimal, so it's actually 0.834.
Yeah.
Okay, so that's a really good average. That means like 82%.
Correct.
What'd you put in? Point.
0.834.
It's because I think it's a little bit off. It's like 0.82. There's something off with.
There's 0.835.
Oh, that's why it rounded, didn't it? Yeah. So that to have an 80% free throw average, that's insane. All right. So why don't you go ahead and go back? We're just kind of experimenting with Michael Jordan for a second. That's all. So go back to the lesson for me. And we're going to end just this part with this Nearpod up here. Suppose that you wanted to analyze the battery life of different companies. Because different companies with different phones, they might have different cell phone batteries. Again, very useful for you guys because you guys love your phones. Would the battery life be discrete or continuous? So again, think about where it starts and where it ends. Okay, if I start at 100%, does it just automatically drop to 0 and dead? Yes or no in your head, and answer if you think it's discrete or continuous. Remember, discrete means you can count every single thing from 0 to the end, or the end to 0, whichever way you're going. Does your you have to ask yourself, would your battery just, it's at 100%, drop to 0 right away? If it does, then it's discrete. If it doesn't, then it's continuous. Let's see what we got. We got a couple different answers. We got a no answer. Oh, we got all answers. Okay, so the answer is B, it's continuous, because you don't turn on your phone when it's all fully charged and it just drops to 0. It goes to 99, it goes to 88.914, blah, blah, blah. It drops down in battery life. There's decimals involved here too. So what we're going to do now for the next 5 minutes is just kind of talk about what I'm going to be expecting you to do, which is what you picked up when you walked in. And just going to summarize some things that we talked about. We know the examples, we don't have to write those down. We talked about relative frequency. It's the ratio of occurrences within an interval. And I want you guys to think of ratio. We can do, there's a couple ways to see ratio. You can see something like 1 to 2. You can see something like 1 divided by 2. You can see, what else can you see? A ratio. And that's it. So those are ways that you can see some kind of ratio. Now, there are two types of things when we talk about statistics. A population. This is something on your blue sheet too to fill in. So that blue sheet, once it's filled in, it's going to be super useful. A lot of the stuff that we're doing the next 2 days will be the blue sheet. So the population represents all possible data of interest in the study. So if I'm trying to make assumption or get a study going on about high schools in the United States, there's no way I can test every single high school in the United States. However, I can come to Lockport and test Lockport. Okay, high schools in the United States would be the population. But the sample would be just Lockport. It's like a little piece of that population, like the guy was saying in the video, a piece of the pie. There's no way I can possibly test every single high school in the United States. I mean, I could. It would just take a very, very long time. However, I can personally, by myself, test Lockport because it's closer to me. And that's what a sample is. So those are two different things. When I talk about population and sample, you need to know the difference between them. A population is the whole entire thing, and the sample is just a piece of it. We're going to practice that relative frequency we practiced with Michael Jordan. So, before we do that, let's read what it says. The battery lives are divided into intervals. There's 100 cell phones that they're testing. So total, you don't have to add all of them up anymore because you know the total. The total is 100%. I'm telling you that in the problem. For each different company, we're testing 100. We want to know the relative frequency. So if I have 100 total cell phones, in order to find the relative frequency, I just need to figure out, well, how many cell phones were there? Only 1 out of 100 lasted 8 to 8.5 hours. So how long do your cell phones last? Because mine don't last 8 hours. Because mine lasts way less than that. Way less. Don't you feel like your battery dies pretty quickly? At least mine does. So what is 1 divided by 100 on your calculator? We just want some decimals here.
0.001.
That's 001.
I got 0. Wait, one.
Got 0.01.
Yep, 0.01. I would accept either answer, 0.01 or 0.01 is fine. Think of pennies. Now, we'll see how many phones last 8.5 to 9 hours. Well, I again do 2 divided by 100. You're taking the amount of phones that we had that qualified for that data and dividing it by the total. It's like taking the average. What's 2 divided by 100?
0.50.
0.50 would be 50 out of 100. You're okay.
Never mind.
Now, what about 17? Come on.
0.17.
0.17. Finish that table. Take a second and finish it. All you're doing is, again, you're testing right now. How many phones out of my 100 phone sample is going to last between 9.5 to 10 hours? So it's like an interval. So between those two, well, 30 phones. So we're starting to get more in the middle here. The more of the average. 30 out of 100. You should have gotten 0.30. Little trick here. It just moves the decimal twice. Hopefully you got these answers. Check them. Do it next time.
I'm confused. Do I just divide it?
All you're doing is you're taking the
30?
number of occurrences, the number of phones, and dividing it by the total. So because I helped you through those ones, do this table. I'm going to write something off to the side. It's the number of occurrences divided by the total. Well, the total amount of cell phones we're testing is 100. Well, so I'm just going to do 1 divided by 100, 14 divided by 100. You're seeing what percent of your sample is actually going to be qualifying for this data. You're asking yourself, what is the probability that I'm going to get a cell phone from this company that lasts between this range? Because it does fluctuate. It does. Your phone might last longer than someone else's.
So
This is the way the batteries are made.
the total is 100.
Uh-huh.
So I do 0 divided by 100.
Uh-huh. And
which
you
is
get,
0.
yep, and then do it again.
1 divided by 100.
Yep.
Which is 0.01.
There you go, and just keep going.
And then 14
check your answers when you're done. Again, the trick is you just move the decimal twice.
Oh, so they're all.
Not this one, but the one before it. Okay. Questions on that part? I'm going to skip around a little bit just because I want to get you set up for the homework, and this is just kind of exploring right now. You will be soon. Okay, we have something called a relative frequency histogram. It's basically like a bar graph, but they're closer together. And I'm actually just going to skip to the next page because I kind of drew them out for you. But we don't need to draw them out. I'm not really worried about drawing out a histogram. So here are what you just did, the relative frequency that you just did. You figured out all of those percentages. Here's that graph that guy was talking about. It's kind of how they look at those curves and kind of figure out what's going on. How does increasing the sample size change in the appearance? So, if you look at this, what do you notice about the data in these graphs? Like, where is a lot of the data at? Where are most of your cell phones qualifying at? In the ends, the middles?
The middles?
In the middle. So, your average is going to be the middle. And you see how it kind of has like this U shape? Something like that. That's important. That's what everything is about statistics. Everything that exists pretty much goes like that. Your average is somewhat clustered in the middle or a little bit off. It can be off a little bit. But then it tails off at the end. Think about heights of people. You don't see a majority of your people in the United States being 7 foot tall. Only a few are 7 foot tall. It's kind of like the same thing in this situation. The last part I just want to talk about is just this piece, because this is the most important piece. The sample size, when we talk about it, we keep increasing the amount. The more people you test, the more accurate it's going to be. So, with that said, what I talked about is this bell-shaped curve. And on your blue sheet, you can fill that in. It says bell-shaped curve. That's a very important term to know, knowing it looks like a bell. Okay, if I put like a little thing here, you can get like your little butler out and you can like ding it, you know what I mean? Okay, so that's what it's called, a bell-shaped curve. Anything with statistics, if it's a normally distributed, is going to look like this. It might be really high, it might be really wide. We'll talk about that more tomorrow and what that means, but you should have normal distribution. If you look at your blue sheet really quick before I let you go, I'm going to zoom in here. Normal distributions come up and peak in the middle and then come back down. This one, if you look here, look, it peaked twice. 1, 2. That's not normal. That data would be like completely not really valid. You'd be like, well, that's really not normally distributed. Just like your test scores. Every time you take a test, I get this data. Everything that we're doing now, I use. Okay, the average score, it's going to be something along the lines of this. Sometimes if the test is harder, it's skewed to the left or skewed to the right, but we'll talk about that tomorrow. But knowing that a normal curve peaks in the middle and has like those tail ends and looks like a bell is super important. This would not be considered a normal distribution. Something like this too, where let's say it looks something like this, and it peaks all the way off to the side. That's not normal either. It has to be peaking right in the middle, right in this middle spot, because that's actually going to be our mean, which we'll talk about tomorrow. Okay, so the last thing I want you guys to do is to start your homework, and I'm going to show you how it's going to get set up for the rest of this unit. It's